In the next 45 minutes, I would like to give the participants a brief introduction to gas turbine power plants. This is today's agenda. So I'll go over the basics of a gas turbine and how a gas turbine operates and where all it is used. And the auxiliary systems will give an idea of what all systems are required to run a gas turbine so that it can produce power or electricity. Okay, and then I'll give a case study on piping design and how a change in piping size will impact like the power generation or like the power output of the gas turbine. I'll also provide some tools and standards that would be helpful, like to even get a basic understanding, not just related to the gas turbine, but in general, like for mechanical and electrical engineers to kickstart their career with. And then I have some career opportunities where if you want to pursue something related to gas turbines, the roles which you can go for, as well as like the companies which hire for this role. Okay. So now I'll go ahead and get started with the basics of gas turbine. So what is a gas turbine? It is simply a continuously operated internal combustion engine, an IC engine. An IC engine is nothing but a heat engine, so which converts the heat to mechanical energy. This occurs in the combustion chamber. So what principle or what cycle does an IC engine work on? So it is a simple Brayton cycle. This Brayton cycle is most of us have learned it like in our basic thermodynamics, the basic principle of Brayton cycle. So I'll go over a little bit on this. So the gas turbine runs on the operation of on the principle of a Brayton cycle. So I have put together a snapshot of like how the cycle works, and I'll go through each step over here. So what are what is the first step? So the first step is uh, like the first step of Brayton cycle is an isentropic process. So we have a PV diagram and a TS diagram to show the same processes over here. So we have entropy as constant and we have pressure as constant, like for the TS diagram. For PV diagram, we have entropy as constant. Okay. So now to start with, what is going to happen in the Brayton cycle, right? So the first thing is a isentropic process from step 1 to 2. So in this step, fresh air is injected into a compressor of the gas turbine. So this, what you are seeing over here, is a basic layout of a turbine. So it has like a compressor, it has a turbine, it has a shaft connecting the compressor and turbine, like which in turn drives the connecting generator. Okay, so here first, fresh air is injected into the compressor, and in the compressor, an isentropic process takes place where the air is pressurized to go from step 1 to step 2 at constant entropy. That means you see your entropy is not changing. That means like no heat or mass transfer is taking at this step, and but you are increasing the pressure. So you are basically pressurizing your injected air. Then the next step will be the isobaric process. Isobaric process is nothing but a constant pressure process. And where does this isobaric process occur? In the combustion chamber of the gas turbine. Okay. And what happens in the combustion chamber? We need heat output to drive the turbine shaft, right? So the pressurized air from compressor is sent to the combustion chamber, and externally we are injecting fuel so that the burning of fuel takes place in the combustion chamber. Okay. And from the combustion chamber, what is the output we are going to have? We are going to have a gaseous mixture which is going to be at a high temperature and high pressure. So what do we want from that? We want the high temperature gas, high temperature and high pressure gas to go into the turbine, run the shaft. The turbine will have like blades which takes the heat, rotates and turns the shaft. Okay, and that is where we are going to get the work output. Okay, but what is going to happen to all the hot air that is going to come out? So we are going to release it as exhaust gases. Okay, so step 3 to 4 is what happens in the turbine is again like an isentropic process. So what we are doing over here, we are going to take like the heat generated and convert it into the mechanical energy or kinetic energy. Okay, so this combustion, this combustion generated gases which are at high temperature and pressure, they apply direct pressure on the turbine blades, like on the engine components. And which engine components? In this case, like they're going to affect on the turbine blades. These blades extract the energy from the high pressure and temperature gas and then rotate the shaft coupling, which in turn will rotate the generator. Okay, so this 3 to 4 step is given over here. And then from what is the isobaric process? Again, the exhaust gases that will be released from the gas turbine. Okay, I'll go ahead and show in the future slides, in the next slides, saying how the exhaust gases can be used. Okay, and now moving on to the gas turbine operation. So this is basically an extension of the schematic. Earlier, we have seen only the Brayton cycle and how it works. So now the next process is going to be how the Brayton cycle works in a gas turbine. So until the turbine, it is going to remain the same process as what I have informed earlier. And from here, the mechanical power is going to drive the generator. And what is the work of the generator? It is going to give us the electricity output. Okay, so through this process, electricity is generated by running a gas turbine. Okay, and from here, like the exhaust gases which you see, which are released from the power turbine, they can actually be used for a combined cycle power plant, because the exhaust gases are actually a high temperature air which is going to come out. So instead of going it to a waste, a lot of power plant owners, what they do is they actually put a HRSG, that is like a heat recovery steam generator, which is basically a normal heat exchanger. What they want to do, they want to take like the hot air from the turbine, gas turbine exhaust, and they would like to use it to produce steam to run the steam turbine. That's it. So that is like a one use which you have of the exhaust gases from gas turbine. But in this session, I'm going to cover like a simple operation or a simple cycle operation of the gas turbine. Okay, now where all are the gas turbines being used? One is just for power generation for your normal grid, like for your household and daily appliances use. So in this power generation plants, like the gas turbines sometimes can be used for base load, that is like continuously provide power to the grid. The second is like peaker plants. So during summers, like when the power consumption is high, the gas turbines which are the power plants which are put on standby, and like they will be brought up for peaker duty, and they will generate additional power that is required. And during the months months or periods which we don't which we don't need the extra power, they'll again go back to being like the standby plants for peaker power. Okay, and the second one is for industries. Like for example, if we see any paper mills or even like a rice mill, and even to run like manufacturing plants, right? Like car manufacturing plants, or it can be any major plants. So where all the power generation is coming from, the gas turbines can be used in that location. Okay, instead of just relying on the grid to provide continuous power, these heavy machinery or like heavy manufacturing plants will have their own power generation plants as well. And then some of the gas turbines called aeroderivative turbines are used for jet propulsion as well. And then electric trains, and then ships, any of like the passenger or cargo ships, like which go on multi-day or multi-month ships, right? For them, for power generation, gas turbines can be used. So within gas turbines, we again have something like which okay, gas turbines, we have the capability to provide power even like from 1 megawatt to hundreds of megawatts as required. For ships and all, we don't need something like which provides 100 megawatt unit. So in this case, like we use something like a small frame or small gas turbines, which provides about like 25 to 30 megawatt power. Okay, and then for gas compression, so we have gas produced in like multiple areas. How is the gas stored? It is basically compressed and stored. How to compress the gas? So we have again like these gas turbine plants to compress them. Okay, and then tanks. So in some of the military tanks that you see, if you can get into some detail of that, you can see that some of the tanks also used gas turbines. So instead of using like the reciprocating engines, if gas turbines are used, like they provide quicker thrust or like they provide quicker power to operate these tanks. Okay. The next, I would like to move to the auxiliary systems. So as I said, auxiliary systems are the systems that are required to run a gas turbine power plant for power generation. Okay, so these are the different gas turbine auxiliary systems. So air intake system, fuel system, depending on the type of turbine it is, and hydraulic start system to run the turbine, lubrication system for lubrication of all the bearings and seals, and compressor washing system, and fire and gas system to protect and detect the power plants from fire, and battery system. I would like to move in detail into each system. So the first I would like to talk about is the air intake system. So what is the air intake system? We need air for combustion. That is what we learned from the basic principle of Brayton cycle. So how is the air being supplied to the gas turbine? Through the air intake system. So that is the first combustion of gas turbine. Then a gas turbine is not left out in the open to run, right? So we need like the turbine to be enclosed. And when we enclose a turbine or a component which is providing or producing high heat, we definitely need the surrounding components to be cooled down so that they function the way it is intended to. And obviously the any of the components that we use are rated to a certain temperature. But as you can see from the basic principle, the concept of gas turbine is to provide like high heat. Okay, so when high heat is rejected, we want like ventilation for all the surrounding components so that it can be cooled down to a required temperature and they can operate as intended. And if there is a generator and a gearbox connected, we have options like to ventilate that area as well if it is enclosed. In case like the generator and gearbox are left out in the open, then we don't need ventilation for this system. Okay, and what are the different types of filtration systems available for the gas turbine? We have something called static filter and pulse filter. So what is a static filter? Static filter is nothing but a filter which you need to use like you need to replace whenever like there is a not whenever, like when the buildup particle buildup is more than the limit, then we need to go ahead and replace. So it requires continuous maintenance intervals. So this is simply like consider like your typical AC vent or um, a cooler vent, right? Like where you have to go ahead and clean the filters every time, like to ensure like it is going to provide the output as desired. Okay, because any type of, if you are not able to provide enough air to the gas turbine, it is not going to have enough media to burn the fuel. So when there is not enough fuel burnt, that means like there is not enough energy generated to drive the blades, and so that again results in lower power output. Okay, and If the other type of filter we have are called pulse filters. So pulse filters are basically self-cleaning filters. So how they keep how they self clean, so they are supplied with compressed air. So compressed air is blowed onto these filters, so that like the buildup will be removed periodically as designed. Okay. And for the air intake system, depending on like where the location of power plant is, we need inlet air conditioning. Like if, for example, the unit is located in a desert area, okay, that means there is obviously extreme temperatures over there. So when we try to operate the plant at an extreme cold temperature, uh, we need the air again to come to a level that we desire. So for that, we need de-icing. So we want like uh, the filters to have like de-icing capabilities, so that like any of the ice that is built up on the filter like can get can melt. And then we have heating coils to ensure like the air is again heated. And then if uh, there is an option to use an exhaust heat, we can use that also to heat the inlet air. Or the compressor is going to provide again like the bleed air. Like, so from the compressor, what is going to happen at a constant entropy, we are pressurizing it. So when you pressurize air in the air, what happens? Like the temperature is going to increase. So we can bleed out the air from the compressor at multiple intervals to use it for conditioning of the inlet air. So this is a typical layout of the air intake system. So here I have a snapshot for a GE power plant, gas turbine power plant. Okay, and the air filter is the one which is located on the top. Okay, so this is basically your turbine enclosure. This is your generator enclosure, which has both generator and gearbox. And then the structure above that is the air filter. So um, coming to the filter, the filter has to be designed to protect gas turbine, generator, and gearbox from the surrounding equipment from which the air is taken, so that we filter out the airborne dirt, contamination, and any foreign objects that to before entering these two enclosures. Okay, now how are they filtered? uh, in addition to the filter canisters like this, in addition to the basic filters we have to ensure that the air filter's life expectancy is increased, we can use some options. Okay, what are the options available? We can have something called weather hoods. So the ones on the extreme right end are weather hoods. So what these do, they protect the filter from any rain, sun, snow, like uh, before the air enters into the filter. Okay, so the way they are designed is so that they can get bolted onto the filter. And if it's a dual inlet air filter, right? From my experience so far, I have only seen like dual inlet air filters. So we have them at both like left and right end of the filters. Okay. From the air filters, we are going to have the air into the filter. And then we have the coil sections. What are the coil sections? They are basically like the heating and cooling coils, which we were talking about earlier. Then we have something called drift eliminators. What are drift eliminators? When air is sucked in, you are not just sucking in the air. Air also contains moisture. So you want the air to be filtered to a particular parts per million. But what if like when you are filtering and there's a heavy, like when there is rain, you're also sucking in like water droplets. So what drift eliminator does is it has basically baffles which uh, filters out like the heavy droplets, and instead like lets in only the finer air particles that are required. And then we have the composite filter canisters. So these are like the finer filters. So, in between, like we also have the pre-filters. So what the pre-filters do, they filter out the air beforehand, so that when it reaches like the composite filter canisters, uh, we have already filtered out the unnecessary particles, so the life of these filters can be extended. So when we have to do periodic maintenance, we'll only do it on the pre-filters. Okay, and not displayed on this schematic, but we also have like ladders and walkways around the filter for maintenance. Okay, then once the air gets sucked in, we want the air to be used for both combustion as well as ventilation purposes. So from combustion, a separate chamber is designed for combustion, so that air is directly injected into the gas turbine. So before it injects to a gas turbine, there is usually a FOD screen. FOD screen is nothing but a screen like which protects the gas turbine from foreign object damage. Okay, and this area like where the air is injected into the gas turbine, it's called inlet plenum. Okay, and then we have other compartments for ventilation air. So segregating the air filter in this way will allow us, will ensure that the required amount of air is going for combustion and required amount of air is going for ventilation. If there is no partition in the compartments, there is no way to designate how much of air is entering into each compartment. Okay, then ventilation air goes into the turbine and cools down the enclosures, both the turbine enclosures and well as the generator enclosure. Now, when it cools down the compartments, you obviously want again like the air to be let out. So we have exhaust, ventilation air exhaust for the same feature. Then the same thing works for the generator. So whatever like the compartments have to be ventilated and exhausted, we have separate ducting, and then we have some separate ducting for turbine exhaust. So this is where after the combustor, uh, once like the energy has been taken to rotate the coupling and the shaft, we have the hot gases remaining, hot air remaining. So what does the hot air do? Like we have to exhaust it. Depending on what the end customer's preference is, this exhaust air can directly be exhausted into the environment, or this can be used for secondary activities like for cogeneration, that is like to ensure other to reuse the air for recirculation into the air filter, or we can also use it in the steam generator, okay, using HRSG. So this is also called waste heat recovery system. Okay, moving on to the next one. The next one is the, sorry, I just wanted to add one more point. So for a small gas turbine which generates like say for example 45 to 50 megawatt, uh, basically the aeroderivative version of gas turbines, they generate exhaust at around 800 degrees Fahrenheit. Okay, and when we have even bigger gas turbines which provide like more than 100 megawatt, they generate like the exhaust air up to 1100 Fahrenheit as well. Okay, moving on to the fuel system. We saw like the air require how the air is injected into the compressor, like what how the air is filtered and then injected into the gas turbine compressor. Now, the next thing is fuel system. So when we provide air and fuel, combustion occurs. So this fuel is used in combustion process of gas turbine. So fuel and air at certain temperature and pressure, they are mixed in a mixing chamber. So even before it the mixture enters directly the combustor, we have something called premixers. So premixers are where like the fuel and air are ensured that they are mixed thoroughly, and at a certain temperature and pressure, they are delivered to the gas turbine. And how they are delivered from the premixer? Using some manifolds and nozzles. Manifolds are nothing like your basic piping, but specifically designed for these purposes. And the gas turbine power plants, what are the different types of fuel systems available? We can either run it on gas, we can either run it on liquid fuel, or we can run it on both gas and liquid fuel, called dual fuel systems. Okay. Uh, so these gas or liquid fuel, they are supplied. Obviously, um, the end customer directly cannot supply the fuel to the gas turbine. They have to supply till the enclosure, and from the enclosure, it is the power plant manufacturer's responsibility to supply it to the gas turbine. Because again, we have to deliver the fuel also at a required pressure, and we have to ensure like it meets all the quality requirements, pressure, temperature requirements, and also only a certain amount of fuel is being delivered. It's not, we don't want like 100% of the fuel to be delivered continuously, because we want the fuel also to burn at different stages. I'll tell in the next slides as to why we need it to burn in multiple stages. Okay. So this customer supplied fuel is delivered to the combustor via fuel manifolds and nozzles. So the gas turbine can be started either on gas or liquid and can operate to full power on either fuel. So there are a lot of times like where you want uh, to start your unit on liquid fuel, because it starts at a faster rate, or it can start generating power at a faster rate than a unit which is running only on gas turbine. But again, depending on how the end customers availability of fuel, they will request these manufacturers to design their power plants. So because of the availability of natural gas around the world, around 90% of the gas turbines are operating on natural gas as primary fuel source.